My name is Raghavan Matabushi, and this is my fourth physics lab. As an introduction to this lab, we experimented with oscillation of the spring and its mass. We calculated the data from the experiment using Tracker, and the data was provided beforehand, and we also used GlowScript to compare the experiment and the computated model that we created. And basically, the purpose of this lab was just to monitor the progression of oscillations of a spring that was attached to a weight. The system and the surroundings. The system is the mass in the spring where energy transformations occur, and the surroundings are the earth, air, and fixed support that interact slightly but do not significantly change the total energy of the system. This gives you a better picture of what the system and surroundings truly was. As you can see, the ball that or the weight that is as it attached to the bottom of the spring is moving, and I did this all on Tracker where I created the coordinate axes, and using that I was able to find the x position and y position, and using that, as you can see, we have the sine and cosine graphs, which are representative of the oscillation of this ball. Some of the code that we had to make additions to in WebPython, we can start up here in the top right corner. We had to edit the initial F gravity vector, which is obviously going to be 0, and then it was only F grav only interacts in the y direction, so that's negative balda m times g, which is just mass times gravity. We had the spring force, which is just ks, which is a spring constant, times s, which is l minus lo, times l hat, which is l hat just tells you the direction. F net is equal to the spring force, which acts in the positive y direction, and the F spring, which acts in the negative y direction. And then the rest of them is just Newton's second law, which is ball dot velocity equals the velocity plus F net over m times delta t. And then we have the position update, which is position update plus ball dot velocity times delta t. And then we had more additions. We had to make L, which is the spring length was ball dot position minus spring dot position, and then you had S was the magnitude of L minus LO, which gets plugged in back up here. And then these are just the formulas that were provided along with the lab in order to ensure that we were doing everything correctly. Over here, as you can see, we have 0.5 times ball dot m times magnitude of the velocity squared, and then we had the UG, which is equal to ball dot position dot y times ball dot m times the force of gravity, and then we have the spring, which is 0.5 times the spring constant times s squared, and then we had total energy, which is the representative of the energy principle, equals k plus us plus ug. Other additions that we had to make were we had to edit the spring constant, and this was all data that was provided to us, which made the lab actually relatively simple. And as you can see here, we've already discussed these lines of code, and we just had to edit the initial vector based on the coordinates that we got when we did the tracker on our app. So here's the graphs. This was the most important part of this lab, and we were basically checking to verify how close our experiment got with the model. And as you can see, we were a small margin of error, and it's representative of the sine graph and cosine graph, starting with different center points. And as you can see, the delta E was supposed to remain constant all the way throughout, which means that all the net energy is equal to 0. And as you can see, we had everything interacting in the correct way. As you can see, delta spring is the complete opposite of delta grav because they are acting in different directions. And yeah, so what if and what does that mean? So the first thing is the energy principle says that the total mechanical energy of the system, kinetic plus potential, should stay constant if no external forces are acting. From my plots, you can see that while kinetic and potential energy trade off, as you can see there, the total energy stays nearly constant, which means that the energy principle is satisfied by my data. And the final thing was when I measured the oscillation period from the x and y, I got about 0.82 seconds for x and about 0.80 for y. So I thank you guys so much. And yeah, I hope you guys enjoyed this demonstration of this lab.